深耕游戏行业10多年，致力于帮助虚幻引擎的用户提升实时渲染和交互的上限。接下来有请 Epic Games 开发者关系技术美工专家 Oztalay 带来他的分享，用您的着色器描绘世界。
Hello everyone, and thank you for coming to my talk. My name is Oztalay. I'm a developer relations technical artist at Epic Games, and today I wanted to talk to you about bringing the world to your shaders. Your materials don't have to exist in a vacuum, and you can do some really awesome things with your materials once you start communicating in information about the outside world. I'm going to show you some examples of things you can do with your materials with that information and a few different ways to get information into your materials, as well as talking about some of the potential benefits. But first, a little bit about myself. I can't quite say that I've worked in the games industry for 11 years since I'm not actively shipping titles anymore, and my time at Epic has me working with users of the Unreal Engine both in and outside of the games industry. It's probably more accurate to say that I developed games for 9 years, shipped over a dozen projects across 6 different game engines, and through all of that I supported and enabled art and design teams to do their best work. And a couple of years ago, I joined Epic Games as a developer relations technical artist, and now I get to empower all users of the Unreal Engine to push the boundaries of the technology through exploration, education, and advocacy. I'm going to be presenting these techniques with the recently released Unreal Engine 5 using both our node-based scripting and node-based material systems. There's going to be 2 parts to each example, the first being how you get the data into the shader, and the second being what you do with it. Former will be using systems specific to the Unreal Engine that exist both in 4 and 5. And what you do with the material, or what you do with the data in the material, should be more broadly applicable to any kind of shading language. There is one thing I'll show you in these examples that is easier in Unreal 5 than it is in Unreal 4. It's very, very small, and it's not impossible in Unreal 4 at all. Otherwise, these techniques exist in both versions of the engine. As an aside about the Unreal Engine, there's an important distinction between shaders and materials, and as much as I will try to use the correct terminology, which in our case is materials, I'll sometimes slip and say shader, and I'm sorry. So the 5 techniques, examples that I want to show you today, demonstrate different methods and pathways of communication into the material. So first, I'm going to show you how to animate the dials on a car dashboard with dynamic material instances. These allow us to change texture, vector, and scalar parameters on a material at runtime. We're going to vary the team colors on a multiplayer shooter's bases using custom primitive data. This lets us store scalar and vector values on the geometry itself. And following on that, we'll drive a swaying chain with information provided by per instance custom data. Then we'll blend decoration into the landscapes in runtime virtual textures. And finally, I'll show you how to project a texture into worlds using material parameter collections, which are global structs of scalar and vector parameters that can be read from any material. For some part of each of these examples, you'll notice that we're going to be shifting some calculations from the CPU to the GPU, and you might be wondering why. Some of these examples are going to help us improve the runtime efficiency, and depending on the situation, there can be a lot of performance benefits to moving certain kinds of calculations off to the GPU. And in one example, we'll end up calculating a value on the GPU just once and reusing that over and over and over again. The other benefit to many of these techniques is the efficiency of creation. Many of these techniques will make it easier to create content by reducing iteration time, or reduce the number of assets we need in the project, or just make things work. With that, let's get started. So let's start with something that's fairly common in the Unreal Engine. There are material instances. These are instances of a material graph that let you change parameters at edit time. And then there are dynamic versions of these material instances that you can create at runtime. And they support changing the parameters or inputs of those materials during runtime. Dynamic material instances are great for situations where you have one to a few things that use the same material and need to frequently react to different inputs. And to demonstrate that, we're going to animate the dials on this car's dashboard with just their materials. I set up a few different dials in the advanced vehicle template that ships with Unreal, and we're going to animate each of these using world position offset, which is effectively an additional function run on top of the vertex shader. Each of these shows a different value because we've got a speedometer, a tachometer, a fuel gauge, and a temperature gauge. So the traditional way of doing this, or the more straightforward CPU-driven way, would be to take all of that information and update the position of the dial component every frame. That, however, can get rather expensive on the CPU, especially if we're trying to do something like this on a lot of these different types of components. Importantly, we don't care about things like collision of the dial, and there aren't any systems that need to look up the rotation of dials. So instead, we can offload that rotation and those calculations to the GPU. To do that, we'll first instantiate the material for each of the dials and set it up with a few one-time parameter updates for the min and max values of the dials, as well as its rotation limit. Then we'll pass the associated information into each of the materials. So for example, the oil temp indicator might only use about a quarter of a full rotation to display values between 120 degrees Fahrenheit and 320 degrees Fahrenheit. But a tachometer can go from 0 to 10,000 RPMs over 3/4 of a full rotation around the dial. Even though we could calculate this on the CPU and just pass a single rotation amount value to each of the dials, I'd much rather handle that calculation a few times on the GPU instead. My goal here is to take as much work off the CPU as possible. Finally, in the material, we'll figure out the appropriate rotation for each of the dials based on those input parameters and rotate it using the vertex shader. And a quick motion sickness warning as I demonstrate this. So here's what we're going to look at. We've got each of the dials set up with temperature and fuel, and as I drive the car around, you'll notice the speed goes up, the RPMs go up as we move the car around, and they drop down as the car stops moving. So firstly, each of those dials is its own separate component that handles passing information to its material. On begin play, I instantiate the material and for later retrieval. Then I pass in some one-time parameter values to make things a little more efficient. We pack the min and max values and rotation limit into a vector that we then pull apart inside the material. We're calling setVectorParameter on the material instance and setting the name to one that we'll set up in the material. Then this blueprint has a function that passes an input display value into the material instance as well. All these dials are going to use the same parameter name, display value. It doesn't matter that this one's the tachometer or this one's the fuel gauge. They all just have a display value. Then in the dashboard blueprint that handles all of the dials, we pass in the appropriate values for each of the different dials. The RPMs to the tachometer, the speed to the speedometer, and this gets called every frame to keep those values up to date. And that's all that's happening on the blueprint side of things. Each dial is its own little blueprint that has all of this logic running underneath it. On the material side of things, I've got this vector parameter set up, and to help myself, I've named each of the channels to match what I pass in from the blueprint. You don't have to do this, I just find it really helpful. This parameter has the same name as the one that we're using on begin play, init params. Then, in order to rotate the indicator with world position, or the vertex shader, we need to get a rotation value between 0 and 1-ish. First, we need to normalize the input display value, but the min-max values that are passed in correspond to, respectively, 0 and the rotation limit, which is a value less than 1 instead of 0 to 1. So for example, again, the oil temperature displays values from 120 degrees to 320 degrees Fahrenheit, but it only rotates about a quarter of the way all around. So that means that a full rotation all the way around would be something like 580 degrees. So we need to figure out what the rotation value, what the displayed value would be at a full rotation of 1. So in order to do that, we normalize the input display value between 0 and the max displayed value multiplied by the reciprocal of the rotation limit, because the max value multiplied by the reciprocal of the rotation limit gives us the value we display at a rotation of 1. Then, of course, just to make sure that we don't rip the dial out of its socket, we'll clamp that value between 0 and the rotation limit. And now that we have a rotation value in the 0 to 1 range, we can use the rotate about axis node to figure out how much we need to offset the position of each vertex. Rotate about axis is great for giving you the delta values you would need to rotate any vector a given percent of a full rotation around a given axis from a given pivot point. I'll have a slide that covers all the math that's happening in this node in the appendix for you to view later. For this, we'll use the object orientation as our rotation axis. That's the vector the current primitive is pointing in world space. And for the pivot point, because this dial is embedded inside an actor, what we really need is the origin of the primitive itself, not the actor. Nor do we want the object position, since that's the center of the bounds of the primitive. So to get what we really need here, we're going to transform 0, 0, 0 from local space to world space. Then the position we're going to rotate is the absolute world position input. This is just the location of the vertex. So to visualize that, we need to rotate this dial at each vertex from the world space origin of the primitive around the object orientation by the amount we calculated earlier. Then we just pass that output of the rotate about axis node to the world position offset input of the main material node. For Unreal, we run a standard vertex shader for each vertex that puts it at the position encoded in the geometry, and we have the option to offset that position in world space, and that's all we're doing here. Of course, if we update the position of a vertex, especially if we rotate it, then its normal is going to be pointing in the wrong direction. That means it's going to light and shade all wrong. And for that, what we need to do is also rotate the vertex normal the same way we rotated the vertex itself. Luckily, we've got a node that does that for you in Unreal already. We'll just hook up the required inputs and pass the new output to the normal input of the material node. Now our dial normals will be pointing in the correct direction based on how much their position has changed. Then you can use this as the world space base normal value and blend any additional normal maps you need on top of this. I've got some references for how to do this at the end of the show. Now, I'd be remiss if I didn't prove out the performance benefits, so I set up my dashboard blueprint to switch between updating the material values and updating the component transforms of the dials. Using the blueprint method added almost 0.5 milliseconds to the game thread on this post-tick update. So you can see here, we're currently using material rotations, and then if I switch that over to component rotations, we start to add a bunch of extra calls to post-tick component update, move component primitive time, and transform or render data. And if I switch back, all of that goes away. So rotating all of these adds a bunch of extra time to the CPU calculations. Now, it doesn't really matter if this is one or two things, but if you add up a lot of things that you move in Blueprint over time, it really becomes more expensive. I spent a little bit of time brainstorming some of the things that you can do when you can pass certain simple state information into a material, and I came up with quite a bit. This is, I think, the most adaptable technique of everything I'm going to show you today, and I wanted to get your heads in the right space before we start getting deeper. There's a lot of different things you can do with this. Cool, so we can make the game modify information on a dynamic material instance. This is really cool. But maybe I don't want to worry about spinning up new material instances and managing them at runtime, especially because each new dynamic instance is a separate draw call, even if you account for Unreal's built-in dynamic mesh batching that tries to group same geometry, same material into a single call. I can use the same material, but modify a value on the geometry instead. If I could look up that value in a material instead of doing it on a per instance basis, then I can still batch all of the same material into one draw call, and I don't have to keep track of a bunch of different instance assets. In Unreal, this is called custom primitive data, and I'll show you how that works too. Custom primitive data is great for situations where you have many things that need to react to different inputs on the same material and can be updated at a variable frequency. To show this off, I've got a very simple FPS gray box here. You've probably heard of programmer art, but has anybody ever heard of technical art level design? On the side of the map, on one side of the map, I've got the blue team, and on the other side, I've got the red team, and we're going to use a value exposed on the primitive or geometry to set the color of the base. And I don't want to have to set up red and blue versions for each of the base construction materials. I want to keep everything as part of the same batched draw call. I also want my artists to have a bit of freedom in creating their maps. This isn't just for red and blue bases. Letting artists set those parameters without having to spin up new material instance assets gives them a lot of freedom and it reduces their iteration times. So first, we're going to expose parameters to the primitive, and then we're going to pass values from the primitive to the material, and then use those exposed parameters to customize asset colors. And it's going to look really simple. So the first step, very trivial. On the material, I've got a vector parameter called team color, and I just check this box that says use custom primitive data. This pipes into a mask that overlays the Jersey barriers based material, and you'll notice that on the vector parameter, it changes to this custom primitive data index 0123. That's because under the hood, each custom primitive data is a single float packed into the geometry. Then under the hood, we can interpret 4 consecutive floats as a vector parameter. Then on these primitives, where we want to use the parameter, we'll add an element to this array of custom primitive data defaults. You'll notice that here in Unreal Engine 5, the vector is pre-populated with the name of the parameter and our material. My colleague Alex Stevens added this functionality for 5.0. And in Unreal Engine 4, you just add 3 or 4 floats here and set the individual values for red, green, blue, and alpha. In Unreal Engine 5, like I said, now we can display these as named parameters and edit them as vectors with a color picker, like so. And now I can just duplicate these meshes throughout the level and change the team color ad nauseum. For testing this one, I just created a set of 7 material instances of the barrier material that used a parameter for its color instead of custom primitive data. Then I set up the 7 barriers below these using custom primitive data and looked at the differences in base pass draw counts as I toggled the material instances versus the custom primitive data. I'll freely admit this technique isn't all that fancy on the material side of things, but I think the performance benefits can be quite substantial. But it's not just about making team colors on bases. Custom primitive data has a variety of uses, and I wanted to show you a couple that I've come up with over the years. You can use these to drive things like wear and tear on an object, or use it to sub-UV select some decals that would be applied to a surface. Most recently, I used it to pass in a sort of bendiness parameter to a Spline mesh racetrack maker. As the start and end tangents of the section diverge, I lerp in that little stepped pattern in order to let the know that the track is curving. There's another way you can pass information to a material through geometry that's specific to instance geometry. It's effectively the same concept, it's just per instance instead of per primitive, like in our last example. You may notice that this lead image looks very similar to the one used for custom primitive data, but the keen-eyed among you will notice that these are instance static meshes and not static mesh actors. So by extension, per instance custom primitive data is great for situations where you have lots of primitives that need to react to different inputs that you define programmatically, but aren't updated all that often. Of course, because we're dealing with instanced primitives, they're all going to be using the same material. To demonstrate this, I'm going to make a chain sway back and forth in the breeze without animating anything. In fact, for this example, I don't even need to update anything on tick. Just like the dials example, we're going to do this all on the vertex shader. But unlike the dials example, we're not going to create a dynamic material instance for each link in the chain. Instead, we're going to leverage hierarchical instanced static meshes, which are instance geometry that can LOD, and per instance custom data to pass the necessary data for the swaying action to each link in the chain. For this example, take for granted that I have a blueprint which programmatically places instances of a chain link along a spline, and that there's controls for this already. In the Unreal Engine, we have hierarchical instance static mesh components which handle a lot of the work of managing a bunch of instances of the same static mesh at runtime, and that's what I'm using here. The benefit for this technique, especially with the Unreal Engine, is that it's going to be far more efficient than a lot of the alternatives. Because we're doing some simple swaying on the GPU, it's going to be faster to calculate that than using fully simulated chains. And because it's going to be a static mesh, it's going to be faster than using a skinned mesh that's been hand or simulation animated. And because it uses hierarchical instance static meshes, it's also going to be more efficient on the GPU than if we had a single large chain static mesh, because the engine will call out the links that we don't see. It's also cheaper because we're just stamping one chain link along a spline than needing a bunch of unique geometry for each part of the chain. And because this is dynamically constructed based on a few user parameters, they're easier to place and chain around. You don't need chain A, B, C, D, E for each situation in which you might want to chain. There's a lot we need to know to pull this off, though. We need to know the axis of rotation, which is just going to be the vector from the start to the end of the chain. We need to get the angle that we need to rotate, which is a function of how far the chain is along the spline. And then we need to get the origin of the rotation. And in order to do that, we need to find the closest point along the start to end vector to each link in the chain. Importantly, how far a link is from the end of the chain is a different number from the closest point along the vector. The good news is that it's fairly trivial to get all this information in print, and because of Unreal's per instance custom data, we can set these values on each instance of the chain through script. So just like the dials, we're going to instantiate a dynamic material instance for the entire chain and pass in the start and end points as vector parameters. Then for each link in the chain, we're going to figure out two important things. One, based on where the link is relative to the other links, how much the link should sway. That's our sway percent. Then, so we can construct the axis of rotation, we're going to use one scalar value that's the percent distance between the start and end points where we find the closest point on the line. That's line percent. We'll pass those two float values to each instance using per instance custom data, and just like the dials, we'll animate those links using position offset. And for those of you who are visually inclined, in order to get the purple point here, we need to know the percent distance along the green line to find that point, and the blue line represents our sway amount here. But not everything needs to be per instance because some of those values are global to the whole chain, like the start and end points of the chain. For that, like before, we create a dynamic material instance and set the start and end positions of the chain as vectors on the material. I'm doing this all in world space to just simplify some calculations on the GPU. So you'll notice I'll transform the endpoint, which is in local space, into world space to do that. On the hierarchical instance static mesh component, I need to tell the engine that I'm going to pass in some per instance data with the number custom data floats value here. This is going to be our sway amount and our line percent. You can also set custom primitive data on instance static meshes, and that will be applied to all of the instances in the component. So line percent is how far along the vector from start to end the chain is placed. Sway amount we're going to calculate based on how far along the chain each given link is. So to get the chain, we're going to use a chain percent value to figure out the sway amount. So chain percent, I'm okay with handling this calculation on the CPU instead of the GPU, just because it only happens once. So in the construction script, we're going to loop over all of the instances to set these values. So the chain percent of the current chain is the number of the current chain divided by the total number of links. That's our chain percent. Then to figure out how much the link should sway back and forth, we're going to remap that 0 to 1 chain percent value between -1 and 1. Then feed that into this little function here, which is the cosine of pi multiplied by the remapped chain percent, divided by 2 and raised to a user-controlled power. And that gives us a graph that looks a little bit like this. I didn't want, it ends up being a much nicer curve than if you did a simple linear interpolate. And I'll include a link for a bunch of really helpful curve equations at the end of the program. So then I can set that 0 to 1 value as one of my per instance custom data floats. I know this is going to be my sway amount, and that's going to be my first custom data float. So that's custom data index 0, and the instance index is the index of the chain that we're operating on right now. Now, the line percent is a bit trickier, but luckily Unreal has a built-in get closest point along a line node. For the point, I just ask the instanced component for the world space location of the instance we're operating upon, and the origin of the line is the origin of the actor. The direction is that start to end vector, and that gives me that closest point along the line. And I can use that to figure out how far along that vector that closest point is by getting the distance between the point and the origin of the chain, then dividing that by the total length of the start to end vector of the chain. Then set that as the second custom data value on the component, and I'll use this in the material to recreate a full vector, since it'll be cheaper to do it there than to take up 3 per instance custom data scalars to do so. In the material, I'll first create the start to end vector and normalize it for the rotation value. For the rotation axis, that's just chain start minus chain end, and normalize that value. Then I'll multiply the unnormalized version of that vector by the line percent we calculated in the construction script and add it to the start position to create my origin, the origin of the rotation, the pivot point of the rotation. And for the rotation angle, I'll multiply sway percent by the sign of the time, then multiply that by a total sway amount that limits the extent of the rotation. That's the one that we're passing in with per instance custom data 0. And I'll also multiply that by a total sway amount in order to bound the rotation. And finally, I'll plug all of those into the rotated axis node and pipe that to world position offset. And poof, chain swaying in the breeze. And the great thing about this is that you can have multiple chains all animating differently at different speeds, and this is all just one single chain link geometry. One limitation of this specific technique is that each hierarchical instance static mesh component will be its own separate draw call. Those aren't dynamically batched together. The benefits here are more about the memory footprint. I use one chain link versus X chain links times all the different chain variations you'd need. So for example, I used a 20-sided stretched torus for my chain link, which you probably wouldn't want to do if you were to have a set of unique chains. But for comparison's sake, that single link was only about 120 kilobytes, whereas one merged chain for all of those links was 4.8 megabytes. The other great benefit is now that artists are more free to chain up whatever they want wherever it is without spinning up new assets every time, or being chained down by a limited selection of pre-built chains. But it's not just about making team colors on bases or animating chain links per instance. Custom data has a lot of really interesting uses. It shines in situations where you're programmatically constructing a lot of objects at once. So you can use it for foliage or scattered rock variation. You can use it when you're procedurally constructing buildings to drive information about different windows and a whole lot of other things. I'm also playing around with the idea of using per instance custom data to drive performance visualizations in a game. Okay, fourth technique, we're almost at the end. This one uses runtime virtual textures, which create their texel data on demand using the GPU at runtime. To oversimplify it, they're large, highly efficient render targets that get rendered into from the top down. This is great for things like landscapes, because many landscapes can get quite expensive as layers stack up. But after an artist is done painting the landscape, these are largely static, so you can offload most of the calculations of these materials to the infrequently updated runtime virtual texture and sample back from that texture set to draw onto the landscape itself. This way, the more expensive and non-dynamic parts of your landscape material are no longer calculated every frame. When it comes to finally drawing a pixel on screen, all you're doing is sampling one RVT at the pixel's world position. There's two sides to how we're going to use RVTs for this example, but for the purposes of consistency, on the read side of things, these are great for when you have many primitives that need to react to the same set of input data that varies per pixel. But that set of input data doesn't have to update every frame. To demonstrate this technique, I will show you how you can blend geometry into the terrain without any additional geometry or having to recalculate material values on the fly. One of the many challenges we've faced over the years is making sure that the static geometry we use to accentuate our landscapes looks grounded and connected to the landscape. I remember chatting with a different former colleague about this as far back as I think 2013 or 2014. My former colleague Louise Kroll showed how to do this with geometry he called dirt skirts at the Technical Artist Bootcamp in 2017. We used this trick to great effect in production in at least one title. For that technique, you export part of your landscape and your whole rock to Houdini, or now in Unreal, you can do this with a the Houdini engine directly. Then you determine the intersection between the two pieces of geometry and extrude that out along the binormals of the rock and the landscape. And this creates a little skirt of geometry with a little alpha around the edges that you apply the landscape material to, or a similarly shaded purpose-built material, and that blends everything together. So what we're going to do instead is we're going to output the landscape material and its height to a texture set, the runtime virtual texture. Then we need to figure out how far a pixel is to the terrain. And then we can use that value to blend between the landscape texture set and the base material. So now, instead of doing something like recalculating the entire landscape material for each pixel of the landscape and for each pixel of the geometry that's blending with it, I can draw the landscape once and sample it in a bunch of different places as a much simpler texture read, which ends up being much, much faster. The reason this works is that RVTs aren't limited to just the material that's writing into them. They can be sampled from other materials. You just need to use XY world position, and the RVT sampler will return the values for the texture set at that location. So the great thing about this technique is that as I move meshes around the level, they're automatically grabbing the nearby parts of the landscape. I don't have to worry about regenerating additional geometry each time I move it. The landscape material is set up to pipe out its base color, specular, roughness, and normal to the RVT output in the material. I've got all the particulars for that output handled under the curtain, so to speak, so this is the key part here. This just means that whenever this material is drawn in the RVT context, output these values to that texture. And that's all we need to do for that. Now I've got the landscape material, and instead of having to do something like run the whole landscape material in blending geometry. But what good is sampling the RVT from a given world position if I don't know where the landscape is relative to my geometry? I have to know where to stop the blend, and I want to do that relative to the landscape itself. As a quick aside, in Unreal, there's this concept of material attributes, which is a giant struct of all possible material inputs that gets passed around the graph, and it's really useful for organizing large material graphs or breaking up complex operations. So that's what that get material attributes block was in that previous graph. So the great news is that one of the other channels of RVT that we can write to is height. This means there's a whole texture that's meant to associate a z height value with a given xy position. And if I write the height of the landscape out to that runtime virtual texture, then I can look up the height of the landscape at any given point in the world in any material. Jumping back to the landscape material, all we're doing is taking the absolute world position of the landscape, masked to the B component or Z, and passing that into the world height input of the runtime virtual texture output node. This means that anytime this material is on a primitive drawn into a runtime virtual texture set to height, this value will be written into the RVT. Easy. What we'll do is sample the height RVT. This is in the object material. What we'll do is sample the height RVT from the current pixel position, which is default for RVT, or which is the default for an RVT sample. And I want a single scalar value that can tell us when a pixel is being drawn closer or further from the landscape and caps out beyond a certain distance. So we'll do a simple normalize here and subtract the world height from the Z position of the current pixel, then divide that value by a scalar parameter so we can modify this on a per instance basis. Saturate that value, which is a free clamp from 0 to 1, but it's less computationally expensive. And that gives us something that looks like this. So it's black when it's very close to the landscape, and it fades to white the further it gets from the landscape. But because I am a simple creator, I need that to make more sense to me. So I do a 1 minus, so that when we are doing the blend, it is a value of 1 really close to the landscape, and it fades to 0 the further away it gets. So now that we know how close the rock is to the landscape, we just need to recreate the landscape material in the rock material. Same thing as before, we just sample the RVT, and we're going to do something with the other pins now. But we're not going to just lerp each of these values in my base material manually. I'm going to show you a cool thing you can do with material attributes. But first off, to demonstrate, if I pipe that material attributes block straight into the material output of the rock, you can see that the rock is just sampling that material. So all we need to do to take our base material and to blend it with our landscape material is the blend material attributes node. And then we can use the distance blending value we created earlier to drive that blend. So here's what the rocks look like with the blend and without the blend. The additional benefit of this technique is that this lets me blend more shallow meshes like these rock clusters, which wouldn't necessarily be possible or feasible with the dirt skirts technique. To test the performance differences between this technique and some alternatives, I created a full screen quad and swapped between two materials, the base RVT blending material and the one that has a material function that blends all the material layers together. Swapping back and forth between those two showed a roughly 0.1 millisecond difference in base pass cost on the GPU for my very high-powered computer. So, potentially marginal benefits, but there are benefits nonetheless, especially if you have multiple draw calls doing a bunch of different things at the same time. RVT blending and using RVT height has come up a lot over the years for me, and I wanted to show you a few other tricks you can use if you know the height or composition of a landscape. So for example, you can use it to mask falling rain or snow, since you know the height of the uppermost thing because RVTs are drawn from the top down. With that, you can also do a sort of faked caustic shadow underwater without having to worry about using light functions or decals. The other thing you can use it for is shoreline detection instead of relying on something that's perhaps more expensive like a depth fade. You can also use the landscape's color RVT to vary the colors on foliage, and the ground color of your landscape will inform foliage itself. You can also, with the height of a landscape, snap vertices of something like tree roots down to the ground instead of having pre-generated assets that you need to try and fit onto a landscape perfectly. Lastly, I want to show you what you can do with material parameter collections. These are global structs that any material can pick up on and react to. It also means that whenever you update these values, you only have to do it once instead of trying to manage it in multiple places. So material parameter collections are great for times when you have many primitives that all need to react to the same values, either once or frequently. And to demonstrate this, I want to show you how you can project a texture into world space using the transform projector object. One of the things we can do with this, for example, is project a movie onto a bunch of particles to really impress and intimidate all of those who seek an audience before our great and powerful magnificence. So let's talk about how that works. I have a screen, like that one, and a projector, like that one. And let's say I projected this 0 to 1 UV coordinate image from the projector onto the screen. Yeah, like that. But this is all well and good, but what if I wanted to look up the UV coordinates on the screen's material itself? How can we look that up? Well, for that, we need to know where the projector is, which way it's pointing. And once we have that, we can transform the vector from projector to pixel into projector space, which will tell us how much that vector diverges from the forward vector of the projector. And once we figure out, and then we can figure out the size of the projected texture would be at any point in the world, because we can't just walk up to the screen with a measuring tape. Then we can make our final UVs by normalizing the transformed vector using the size of the texture at that point in the world. So why are we going to do this? So the great thing about this is that any material can use these global parameters. We set the value once, we get to sample it in many places. So I can use this in multiple particle effect materials with only one material function. So coming back to the problem, what we know is the FOV of the projector, there in purple, the projector's location, forward, up, and right vectors, and where the pixel is in world space that we're going to draw. So we can set up a material parameter collection called MPC projector and set 4 vector parameters for location, forward, up, and right. And there's a scalar parameter for FOV. I created a blueprint based off the camera called BP projector. Every frame, it uses the set collection parameter pointing to that MPC we created to pass in location, forward, up, right, and FOV. And we're taking all of our known information and sending it along to the material. This is all we need to do on the blueprint side of things. On the material side of things, I'm just going to build all of the UV logic into this little material function that you can reuse in a bunch of different materials. This is going to output the UV values I can use in any way that I want in other materials. So the first thing we need to do is make sure that we're always operating in projector space so that as the camera moves, the projection follows it. Because again, we're trying to figure out how much the projector pixel vector diverges from the forward vector of the projector in the projector space. Unreal doesn't have the ability to construct and transform vectors into arbitrary spaces though, but it does have this inverse transform material function, which is basically the same thing when you pass vectors in that define the space. So quick background on matrix multiplication. So our input vector is a 1x3 matrix, and our three basis vectors will create a 3x3 matrix. The resulting matrix is a 1x3 matrix that basically is the dot product of each column of the basis vector of the basis matrix with the vector. So this function is basically just dotting the input vector with each of the basis vectors and using that as the components of the output. So it dots invec with basis x to get the x component, and so on. We can skip trying to make a matrix with all of the built-in nodes and just handle the components of matrix multiplication as we need them. So also a quick refresher on dot products. Dot products return a scalar value that tells you basically how aligned two input vectors are. If the vectors are perpendicular to each other, the values are 0, and if they're totally opposite, then the result is negative. And if they're totally aligned, the result is positive, and we can leverage this. So we just need to take the vector to transform, and that's just world position to projector location. A quick note, when you're sampling values from a material parameter collection, they automatically come in as float 4s, so I just mask that out to XYZ. Now, this is the space we're constructing might look strange. Why would I use the projector's right axis as the basis x? Well, remember how dot products give us the alignment of two vectors. The resulting vector of this node is the pixel to projector dot basis x. So if I want the x value of the resulting vector to tell me how aligned the pixel projector vector is with the right vector, so as the pixel projector vector moves to the right of the projector's forward vector, the value increases. Similarly, I want the y value of the resultant vector to give me the alignment of the pixel projector vector with the up vector of the projector, but I want that value to increase as it goes down and decrease as it goes up, so that's why I invert it. Finally, to round out the space, we need the forward alignment to be the z alignment. Now, this is where it gets fun. So if I mask out the z component and normalize the transformed vector, what I get is an x component that increases from 0 to 1 as the pixel projector vector goes to the right of the forward vector. I also get the y component that increases from 0 to 1 as the pixel projector vector goes down below the forward vector. And these look an awful lot like UVs. But because I want my projection to be sampled with a 0.5.5 over the forward vector, I should be able to just subtract 0.5.5 from this normalized transformed vector to get what I need, right? No, because we can't just normalize the transformed vector against itself. The pixel projector vector isn't a unit vector. It's got magnitude equal to the distance between the projector and the pixel. And at that, it doesn't account for the FOV of the projector. This vector wouldn't give us a 0 to 1 space until it reaches full down or fully right, which isn't helpful for us at all. In order to properly offset and normalize the vector to the 0 to 1 space, we have to know how big the texture would be as if it was projected from our projector. We need something to divide it by. So we've got the pixel projector vector, we know how long that is, and we know the FOV of the projector. But I don't know about y'all, my brain's starting to hurt, so let me flatten that out, because sometimes I think it's easier to solve a problem if you can just drop a dimension. Right, so I've got A, which is the pixel projector vector. I've got theta over there, that's the FOV of the projector. I just need to solve for B. And sometimes I like to doodle when I'm problem solving. So if I extend lines from the projector out to the screen where the screen should end, that starts to look an awful lot like an isosceles triangle. And I remember from high school that an isosceles triangle is just two right triangles wearing a trench coat. And if I remember my high school trigonometry at all, I know that you can learn a lot about a triangle given only the length of a side and one angle. And I know the FOV, and if a triangle is half of an isosceles triangle, then I guess that means that this angle is half the FOV. And I know the length of this side of the triangle, that's the distance from the projector to the screen. So if I can just figure out this other side of the triangle, I should be in good shape. I guess the side is opposite of the angle, which would mean that this side is adjacent the angle. God, I really wish I remembered high school trigonometry. Wasn't there some kind of acronym that was supposed to help me with this stuff? Oh, right. SOHCAHTOA. Oh, okay, really had to dust off some stuff there. So what SOHCAHTOA tells us is what values we can figure out about a triangle based on what sides. So we're going to use TOA here, which means that the tangent of the angle is equal to the opposite side divided by the adjacent side. And doing a bit of algebra, that means that the tangent of the angle multiplied by adjacent is equal to the opposite side. Okay, let's get back into Unreal before I get scared. So we're passing in the FOV of the camera, and all we have to do is halve that. Then we can get the adjacent side as the distance between the pixel and the projector. Make things a little more clear, I'm using these new named reroute nodes. That's going to help me keep track of things in the material. Now, a quick note about trigonometry operations in Unreal. Our material tractions are in period 1 or unitless. This is a big difference from your graphing calculator, which uses a period of 2 pi. I graphed a sine wave in period 1, which is this red line here, and period 2 pi, which is this green line here. So if I wanted to convert something from degrees to radians for a graphing calculator, 1 radian in 2 pi is 360 divided by 2 pi, or about 57 degrees. And for period 1 radians, a radian is just 1 degree. Which means that in order to convert our FOV's degrees to radians, we just need to divide it by 360. Then multiply the tangent of the FOV by the adjacent to get half the size of the texture at the adjacent distance. Now that we have the size of the opposite side of the triangle with half the FOV, it means the full size of the projected texture is just double that. And because right now our UVs aren't centered at 0.5.5, we need to bias it over by half the width of the texture and dividing that by the full width of the texture to get values from 0 to 1. And taking a look at that in preview, it looks like our UVs have shifted so that 0.5.5 is right over the forward axis. And for the sake of clarity, I just masked out everything beyond 0 to 1. Then all we have to do is use that in a material function to output the UVs into a texture sample. So for example, this is all I need to sample a looping video for our man behind the curtain. From here, I can plug this into the rest of my emissive stack to blend it in however I need to. And behold, all these particle effects are using the same material function created earlier to sample the little video of our wizard's face. All of this is happening in the particle, and none of this is happening with more expensive alternatives like light functions. Speaking of light functions, in Unreal, you can apply a material to spotlights, so why are we not using that? This was an awful lot of work. Light functions have a few limitations that didn't make them perfectly suited for this. For example, light functions are grayscale. They can only change the intensity of the cast light, not its color. So for a full color projection, you need to place a red light, a green light, and a blue light, all with the same materials. Which can be complicated, since adding a light function to a light means it will be treated as a shadow caster and dynamic. This may be prohibitively expensive for your performance budgets. Instead, with a little bit of information about the outside world, you can look up your texture in your receiving material with a bit of math and without the overhead of shadow casting lights. To test the performance here, I again set a full screen quad with 2 different materials. one that displays the projected texture, like we were doing with the particles, and one that's just default lit gray material. When I swap to the gray material, I switch to a three spotlight setup that are each showing red, green, and blue light respectively, along with a light function that's just playing the video. The difference in the base pass cost is negligible on my machine, but the light function version added about 1 millisecond between lights, shadow depths, and shadow projection. This has actually come up a few times for me over the last couple of years, and it's been a surprisingly useful tool in my tool belt. So I thought I'd share it with y'all today. Here's a few ways I used it, and if this talk inspires you at all, I'd love to find out how you end up using it as well. Before I wrap up, I gotta say a few thank yous and acknowledgements. I don't think I would be standing here today were it not for the groundwork laid by Ben Cloud, upon whose mighty shoulders I hope to one day stand. I'd also like to give a big shout out to the team at Quixel, whose assets I used in landscape demo. And finally, a big thank you to my colleagues at Epic Games for their invaluable feedback on this presentation. One is, how do you handle LODs for the individual chain links? Do they LOD together or separately? So in the Unreal Engine, we have two different kinds of instant static mesh components. One is called Instant Static Mesh, and all of the instances are called an LOD together. And then there's hierarchical instant static mesh components, which is what I used for the chain, that individually LODs and culls each instance. And those are very valuable. What tips could you give for constructing the chain spline? So the very, very simple technique for constructing the chain spline, here we go. I just take a couple of vectors that point to a little slump point, and I figure that out. You would probably want to use something more like a catenary calculation to create a more accurate slump in the chain. This one was the technique I used was a bit more straightforward. And what are the limitations to the method that you've shown for blending objects into the terrain? Now, let's go back to this. So one of the limitations here, and you may notice it, is that there's a bit of stretching on here, and because of the normals that we're blending with, it doesn't quite hide that seam, that tiny little seam there. And you can do a little bit of extra work in your material, create a sort of lip, blends between the two, the surface normal here and the surface normal here, to create a little sort of ridge, almost like a footboard or a toe kick kind of thing, just to create a little lip to blend everything together, which I think can be very, very useful as an extension of the technique. The other thing to watch out for is that to make sure that you're properly blending the normals together, because blending normals can be a very key exercise. And with that, thank you all so much for watching. I really appreciate your time. Have a great day.